to another episode of Space Science with Python. Today we are concluding our asteroid reflectance spectra project with script number 14, and today we want to try to verify whether our GMM algorithm that we created last time makes sense or not. So the question is, or the premise last time was, that the latent space data are drawn by multivariate Gaussians, and we played around with the Gaussian mixture models. We used the Bayesian information criterion to find the best number of Gaussians that describe our data. And in fact, you could say, well, I'm done now. I have my clusters, my unsupervised clusters, and that's it. But we should also test or see whether our data are drawn by Gaussians at all. So this is what we are going to do today. And then afterwards, the summary and the outlook, I would like to talk a little bit how the future of this project will look like. Now, today's session will start at cell number 15, so you can jump directly to it. Here in Colab, this feature, it does not work. You can't just click on it and then it jumps there. It only works in Jupyter Lab or in a Jupyter Notebook. So let's go to cell 15. This is the autoencoder part we did last time, the signal reconstruction and so on, the Gaussian mixture model from last time, and then we should be in cell number 15. There we are. Now this is the confusion matrix we worked on last time, where we saw that, for example, here this GMM class called C0 corresponds to the S class, or a lot of S class asteroids are being assigned to this C0 class in this GMM clustering part. And now we are checking whether this class makes sense or not. So let's start with cell 15. In cell 15, in general, I would like to see or check only the S class today. So not all the other classes, but only the S class, because this is the most significant one. So here we are just assigning or taking the S class the data and group by our GMM class. And what we see is that around 430 S-class asteroids are assigned to this GMM class 0, around 100 class 2, and 22 class 4. So let's take a detailed look at GMM class 0 and see whether this data here describes some kind of multidimensional Gaussian distribution or not. So how do we do it? Here in cell 16, we are now taking a look at the different probabilities also of the Gaussian classes. So we have here the C0 class, C1, C2, C3, and C4. And what we want to see or take, we want to take the bus class, S class, and also considering the C0 probability. So we will only take probabilities or S-class spectra that have a high probability, that are high probability of being a C0 class. So we want to take the bus class S and the GMM class 0 that have a high probability of being C0. So this is what we are going to do, and these data are then used for our Gaussian check. So here let's quickly take a look at our C0 distribution, the probabilities of these C0s with the main group S. And this is just a plotting routine here in cell number, what was it? Cell 16 or no, 17. And here we see that, all the data are just scattered between 0 and 1, so 0% and 100%. And we see a lot of data over 250 are between 95 and 100%. So we only take a look at this high probability, bars. We only consider the S-class asteroids that belong to this particular bar. And this is being done in cell number 18. So this is here where we just say, okay, please just give me the S-class asteroids with a probability of larger than 95% that are being assigned to this C0 GMM class. And this is now our next data frame. It's basically the same as before, but we have here our C0 classes or probabilities that have at least 95% or 0.95 respectively. Now, the question is, okay, what do we want to do to determine whether these data here, this latent space, draws some kind of Gaussian distribution or not? And for this, we use a new Python package, which is called Pingouin or so. It's not Pingouin, it's written a little bit differently, Pingouin. I don't know how to pronounce it correctly. Just a quick note, if you are installing it in Google Colab, it also installs another version of SciPy, and then it happens that an error spawns when you import Pingouin, so you have to restart your runtime in Colab, but then everything should work. So just a small warning here. So in cell 19, we are installing Pingouin and also importing it. And what is Pingouin? It's, yeah, it says here, it's an open source statistical package written for or in Python 3. And yeah, it works with pandas, with NumPy and so on, and it adds some functionalities that are not in, for example, NumPy or SciPy for statistical things. Yeah, so there are a lot of different things. Just check out the API. A lot of, yeah, it's basically a statistics tool. And one of the tools that are there is the so-called multivariate normality. And here they check whether the, this function checks whether the data is, describes a multivariate normality. So it's based on Henze and Zirkler. It's a paper from 1990, I think. Yeah, there it is. So all the details can be checked there. And it's like all the other statistical tests, you provide a data set, and then it also checks the p-value, and depending on the p-value, I think limit at 0.05, it checks, it says whether, whether the data is has a certain probability of being drawn by a normal distribution, by a Gaussian distribution or not. So it provides this HZ value here, and this p value, and then simply a human readable answer whether the data is being drawn from a multivariate normal distribution or not. So simply normal, true or false. And this is what we are going to do. So be aware though that there are a lot of different tests, and I just picked up one, some random, not really random, but I picked one of the statistical tests to show you, or also to emphasize in this video, that when you are finishing your data science project or your machine learning model, verify that it makes sense. So we just used GMM without even any thoughts and said, yeah, GMM looks nice, let's do it. But we will see that maybe GMM is not the best solution in our case. But still, let's have a look. Okay, so that's basically it. So here now in the next cell number, this is 19, cell number 20, we are just simply calling this function now here. Now you have to be aware of the dimensionality, of course. So it's the number of samples versus the columns or the features. This is given by the structure of our pandas data frame, where we also provide now here our D type in this NumPy array, and then we simply call this single function, this Pingouin multivariate normality, and we see the p-value is really small, and the answer is, well, the S-class main asteroids, they are not drawn by a Gaussian five-dimensional Gaussian distribution, or let's say the probability is really low that these data points are drawn by such a multivariate Gaussian. Now the question is, of course, okay, how can you continue with this? Well, consider the video from last time, from yesterday, with the clustering, different clustering algorithms, play around a little bit. But I think here I wanted to show you a negative example, because negative results or examples are also results and examples, especially in science. And this is how I would like to conclude the asteroid reflectance spectra project. So this is basically it. You have now a lot of scripts you can play around, but the question is, what's the outlook? What are we going to do next? Well, my YouTube channel and also the tutorials, they have a default part, I would say, where I show sometimes, or before I created this small sub-project, different concept in space science with animating asteroids or comets, computing the gravitational attraction between planets using SPICE and so on. And I will continue with these videos. So I will just throw in some new space science related tutorials and topics all the time. But I would also like to continue this kind of project style or project-like style. And this project thing, the next one will be about near-Earth objects, so NEOs. Just write it down here. And there we will take actual data, we will take simulation data, and we will see where the objects are, how can we observe them most efficiently. So how should we design our telescope. So these are questions that should lead to an answer. What is the best observational strategy to find or discover as many NEOs as possible? Because NEOs are objects that can have a close flyby or encounter with our home planet, and it's also part of a space situational awareness where we would like to see what is our space vicinity doing, the space weather, solar wind, the asteroids, space junk like the space debris and so on. So this is a very hot topic, and I would say we focus on NEOs next time, but also in the meantime I will throw in sometimes some other I don't want to say it's out of context videos, but more this default tutorial part. Maybe, and this is maybe something I would like to hear from you, throwing in also actual space science. Actually, I prepared already some videos, but I was not really sure whether I should show them on my channel or not. It's about simple space topics where I just explain, for example, what is an active asteroid or other less common known concepts. I don't want to talk about things that have been explained thousands of times, but more like the more unknown topics with simple some presentation and some my drawing skills to show you some maybe less known space science facts. But you can just maybe write me if this would be of interest or not. I'm still a little bit unsure whether this fits in this YouTube channel. Okay, so we are done with this session. I would say we are done with the asteroid reflectance spectra. I hope you learned something from a data scientific view, from a space scientific point, and also you learned something about asteroids or asteroid reflectance spectra or spectra at all. We will still continue talking about asteroids, especially in the next session about near-Earth objects, also about the orbital elements and so on. But I would say for now, let's call it a day. Let's conclude our project, and I hope you enjoyed it, and I hope I will see you also next week. Take care.